First thing I'd like to do is just let you know that 6 months ago, I moved from Seattle to New Zealand, and I kind of knew it would be far away from Europe, but now I can say with certainty, it's really far away from Europe. So I start heading home on Sunday, and I'll arrive on Tuesday. Yeah, so I'm in Wellington, and it's winter down there, so I heard everyone complaining about the weather, and I think it's great. All right, so I spent 18 years at Microsoft and 15 years on the Xbox team, and I got to do 3 big things. I got to found Xbox Live and run engineering for it for about 4 years. And then I ran XNA, which was the developer program, for about 5. And then I ran the operating system team for Xbox One. After that, decided to go do something else, took a break, and really found myself thinking a lot about what were the things that I'd learned while building consoles and being in the game industry. And when I look ahead, I see that there's several big trends that are happening. We hear about IoT, the Internet of Things, and we hear about new kinds of devices, and there's going to be lots and lots of them. And one of the realizations that I had was that consoles are really just big, fat, hot, plugged-in IoT devices. They're managed like an IoT device. They have security issues like an IoT device. And when you deploy them and you think about what software is on them, they look just like IoT devices. So what are some of the lessons that we can learn from looking at consoles to give us an idea of what's coming in the next generation of computing devices? So that's kind of what I'm going to talk about. My goal is not to have anybody be an expert in any of these areas, but to give you an idea of these are some of the things that you might want to go further into as you're looking at these new realms of software and development. We're going to do it in a couple ways. We're going to look at some actual hacks that happened against consoles. We'll think about the implications of those hacks, and then I have a few thoughts on what we can do. Right. So let's talk about goals first. In the normal PC world, the defensive stance is that you've got a user using a PC, and there's an unknown attacker out somewhere across the internet that's trying to steal their bank account information or get other information from that user. It's completely different in a console world, where the owner of the device has usually paid the attacker to solder something onto the motherboard and compromise their own device. Right, so there's a difference. In PC world, you get to assume there's some level of physical security. And in the console world, you don't have it. You have to think a little differently about the defensive stance that you're going to take. And this difference underlines all the ways that we think about security in IoT. And by the way, I really don't like the name IoT because the S in IoT stands for security. Right? So I prefer connected devices. And that's kind of the way to think about it. Unlike a PC, a connected device does one thing. A PC could run any software. You're going to put whatever software you want it, but a connected device was built for a purpose. It does one job, and that's all it's supposed to do. So let's talk a little bit about motivation. Why do people attack their own Xboxes, their own consoles? And then we'll go into what those attacks were. The first goal that someone has when they're attacking their own box is to play free games. Right? There are restrictions on these boxes for business model reasons that make it difficult to change the games, to get rid of the copy protection, to change what the code in it is. And of course, it'd be nice if you could just play free things. So this is one of the motivations people have to solder chips and make changes to their console. The next is they want to cheat to win. It's not good enough to play free games. I want to win. I want to be at the top of the leaderboard. So people will change those games, and they'll put in things called aimers, which you take an action in a game, and it'll correct whatever you did, and you'll always hit, right? Or mappers, or other types of cheats. Or perhaps they want to repurpose the box altogether. One of the things about a console, and this is also true in connected devices, is that they're very efficient in terms of computing power per money spent. On a PC, you spend a lot of money, and you get a device that can do anything, In fact, if you're really into games, if you want the best game, you go buy a PC because you can buy a video card that is tremendously more powerful than the video card in the current consoles. But you're going to spend a lot of money for it. Because the console only does one thing, it can be very efficient. There's no printer drivers, there's no web servers, it's just the game. And because of that, then the game console companies sell it basically at cost, and they make their money selling the games. So if you can take that device, which is very efficient for the money, and get it to do something else, that could be a win for someone trying to cheat the system a little. So let's talk about some actual attacks that we've seen. Now, these are all attacks that you can look up and you can read about. There's others that didn't make it to the public, and I can't talk about those. But these are all very interesting ones that we can learn from. The first comes back from the first Xbox. I used to call that Xbox One. I can't do that anymore. Right, so we'll call it Xbox Prime. So the first attack is from the era of the Prime Xbox. And the goal of this attack was to repurpose the box. There was a really popular game, and they did an innovative thing where when you're playing and you saved your position in the game, it would write out a file to this memory card and take a snapshot of the screen and write that down as part of the save game. And the idea is when you come back to play your game, you could look at the picture and you know where you were. But they didn't sign it. They didn't put checks on that image. So you could take the card out, stick it in your PC, modify the metadata of the image, creating a buffer overrun attack that would happen in the Xbox. And then there were tags, metadata tags, in the image which contained a Linux kernel. So what you see is someone had put that save game in the box, started the game, chose where they were going to resume playing, and boom, you're running Linux. That was an eye-opener. Let me see, the next attack. The next attack was really interesting. So this is a 360 era attack, and this one's called the glitch attack. The glitch attack blows my mind, and there's some really interesting things to learn from it. We changed the way that the games launch, and we took a bunch of precautions so that things like changing those images wouldn't work anymore. But the hackers were very clever about it. Now, the goal in 360 was to make it so that you can always attack a device if you have physical access to it. The goal was to make it so it would be more expensive to hack your box than it would be to just buy the games. Right? So that's the goal. And we figured it would probably take several $1 million for someone to cut the top of the chip off, run an analyzer on the circuitry, and then come up with something that would work. And what we didn't necessarily figure was that they could tap into the lines on the motherboard and actually watch the instructions flowing across as it pulled in from memory. So what this chip did is, as the game is running and launching, you scan it, you make sure it hasn't been changed, you run a cryptographic signature and check it in against data that's in a certificate, and at some point, there's a register on the CPU that either has a 0 or non-zero. If it's non-zero, that would mean failure, and in this case, a 0 meant success, the game can play. So this chip would watch the information flowing across the bus, get the timing exactly right. That check's been made, the value's in the register, it's about to do a check against the register, drop a voltage on a pin, clear the register, bring the voltage back up, execute the branch, everything's good. The lesson there is that you can't trust the hardware. When I think about modern attacks, what are the types of attacks we need to think about going forward? It's starting to get difficult. If you have a device with unified memory, that means that the graphics memory and the CPU memory are the same pool of chips. Right? This is common in consoles, this is common in phones, and it's common in IoT and connected devices. This means that both devices can read and write from memory, which means you can, in theory, write shaders that would go and inject CPU code into memory that should otherwise be write protected. And you have to think about that sort of world. We have to worry about side channel attacks. These have been in the news lately, the Meltdown and the Spectre attacks. And in the last 2 weeks, I saw some articles go by about 6 more side channel attacks. And these are crazy. And they're really difficult to explain, but I have an analogy. A side channel attack is it's like you're going to your favorite coffee shop every morning. And you could say you go at 8 o'clock in the morning pretty consistently, and you like cappuccinos. So you're going to order a cappuccino, and the coffee shop's goal is to get more customers through more quickly so they make more money. Well, they've noticed that for 5 days in a row, you've come in and ordered a cappuccino at 8 o'clock. On the 6th day, you get there, and they say, you don't have to wait in line. We've already made your drink. It's on the counter, because they've recognized the pattern. You get to go skip the line, you pick up your drink, and it all works because they've already written your name on the cup, they've got your phone number on the cup, and they've written your bank account information on the cup so that they know how to pay for it. That's great. For like 3 or 4 days, you just walk into the coffee shop at 8 o'clock, you go straight to the counter, you pick up your cappuccino just as it lands, and off you go. Now, the 5th day, you've changed your mind. You'd like an Americano. So you go to the coffee shop, you stand in line, and by the time you get to the front of the line and you tell them you want an Americano, your cappuccino with your name and your phone number and your bank account has been sitting on the counter, and everyone who walks past can see that information. Right? When you order the Americano, they take that one off the counter and make your actual drink. This is what side channel attacks are doing. The CPU is predicting and noticing patterns in what your code is doing and looking for interesting things like, Bitcoin wallet math. I see you're doing math on this thing over and over and over. Well, I'm going to pre-calculate it and stick the answer in the cache because I can predict you're about to come and ask for it. But then when you don't, your Bitcoin wallet is sitting in the cache and other applications can see it, and you've just lost information. Right? These are really difficult attacks, and they come down to the very nature of the chips that we use. Another kind of attack that I worry about is machine learning attacks. Now, every driver that you load into your kernel, you go buy a printer, and the first thing you have to do is load the driver in. You have to load the driver for your printer into the operating system. That goes into the kernel. And that's a big, complex piece of software that you don't know who wrote it, and you don't know where they wrote it, but you've just loaded it into the most privileged part of your computer. It can see and do anything. It can see all the memory. It can change anything it wants. Now, let's assume that the people who wrote that driver have good motivations. They're doing everything correctly. It's still complex, and there's still going to be bugs. Attackers are starting to use machine learning systems to scan that software and use these systems to find the flaws, whereas previously you had to look at it by hand. Now you can start to build machines that look for these flaws for you. And then another one that blows my mind is, it's probably a more formal name for it, but I'm calling it signed code constructions, where you take code that's signed, it's legitimate code, they're doing everything they can to prevent it from being modified, but if you can change the data that's on the stack, you can be in a legitimate signed function, execute it correctly, but return into a different legitimately signed function, but in the wrong place. And in this way, you can scan a large body of code and start to find jumps between official functions that would build effectively a Turing machine out of code that you didn't actually write. Right? These things have to have machine learning systems to find it out. It's way too complicated. But the new modern classes of attacks are getting very difficult to defend against. So what are the implications of these style of attacks as we go forward? Okay, the first one is we have to change the way we think about hardware. And this is really important because we've all been trained as software people to think about the data and to think about the protections we're doing against the protocols that we're building. But in the connected devices world, in a world where these devices are in the field, where you don't necessarily have protections on them, you cannot assume the hardware is untampered with. Okay? You've built, I don't know, let's say you're building a computer that's going to drive water pumps for a city. It's out in the field. Someone could break into the room and solder something onto the motherboard. Or you have a windmill, or you have a valve, or you have even simple things like temperature sensors. These all become vulnerable when you don't have physical security. So, number one, you can't trust the circuit board. This means that data flowing over any kind of trace that's on the board is going to get tapped. Somebody, if the data is valuable enough, will walk up to that device with a circuit analyzer, attach it to the pins, and watch the data flowing over those wires. So don't put secrets in places where they flow over the wires. Number two, you can't trust memory, and you can't even trust registers in the CPU. We already see that from the side channel attacks. Main thing, again, is don't put secrets in memory. If it's addressable, it's going to get stolen. If it's going into registers, it's going to get stolen. You basically can't trust any secrets in the CPU. I am not saying you can't run code on the CPU. That's fine. But don't run anything on the CPU that you really need to stay secret. As you write software, you have to assume that your memory's been compromised. You have to assume that that data on the buses have leaked, and most of all, you have to assume that every driver is an attack vector against your machine. Right? Again, this is a little bit easier on PCs, but these are the realities of what we face in the next trillion or so devices which are going to be in the IoT space. Okay, what can we do about it, and what are some of the implications? Okay, let's review our goal as defenders. First goal is that the cost of an attack is higher than just compliance. So I went down to the city of Christchurch, the district is called Canterbury, and spent a couple days down there, and I'm talking to some of the council members, and they're very concerned about CO2, about nitrate runoff from the farms. Basically, they're very worried about environmental degradation in the area. So they have this idea that they're going to build devices and maybe put them out in the streams and put them in runoff areas and start to measure what's the runoff and what's the output coming from various forms of industry. And that's great. But you have to ask yourself the question, is it easier for the person you're regulating to comply, or is it easier for them to just change the data? Now, go back to that glitch attack. We assumed that it would cost millions of dollars for someone to go and analyze the box and figure out what that attack would be. Correct. No gamer did it. But there was a company in China that did, and they boiled it down to a little chip, which they sell for about $80, and that's less than 2 games. Right? So you have to assume that if somebody can boil it down, they'll make that investment and then create a little chip that you can just solder onto the board, and you're done. So, goal, keep the cost of the attack high, but it depends on the next goal, that a successful attack against one device should teach the attacker nothing about the next device. So, I'm going to make you spend the large amount of money to do that analysis. I want to make you take the top of the chip off and use a focused ion beam or whatever to read the values of the transistors, and then I want to make you do it again for the next box. Right? This type of goal is not enough for classified assets and military type things, right? Because then the value of a single device is super high. But if we're talking about industry, we're talking about farms, we're talking about water pumps, that probably is good enough. And then the third goal is that when someone attempts to do these things against your device, you want to make those attacks visible on the network so that you can have your systems running in the cloud and start to get flags popping up about devices. Oh, that one's showing anomalous data. I need to better go send someone out to go take a look. So what can we do? First piece of advice, if anyone is even remotely interested in IoT, in connected devices, and you probably should be because they're talking about billions, if not trillions, of devices that are in mission-critical systems, I want to recommend people start studying FPGAs. That's a field programmable gate array. And I've heard about these things for decades. I'd never wrapped my head around it until recently. An FPGA is basically a bunch of transistors, just like a CPU, except there's no instruction built into them. A CPU is a bunch of instructions, and that's all it can do. When you have an FPGA, you basically get to make your own instruction that you can add to the set of instructions in the CPU. So what would you do with that? Could I make an instruction that inherently has my keys in it and does my math for the cryptography? That would be pretty cool, because then I can still do my cryptography, I can still do my blockchain math, and I never have to have those secrets held in RAM. They never go into a register because they're not in addressable space at all. They're burned into transistors on an FPGA that then gets treated like it's an additional instruction that's been added to the CPU. You can go the next level if you want, and this one really blows my mind. A puff is a physically unclonable function. And you can look these up and read about them, and they'll blow your mind. Normally, when CPUs get made, they take a piece of silicon and you put some other chemicals on it, and then you put a mask which has a pattern on it, and you shine some light through it. Then you do another mask on top of that one, and another mask on top of that one. And slowly you build up material which becomes the transistors of your CPU. Those masks are never perfectly aligned. There are quantum fluctuations which cause them to vibrate as you're making the chips, which means sometimes they're really well aligned and sometimes they're not. This is how they choose the different clock speeds for the chips that you buy. The expensive ones were made on the same process as the cheap ones, but then they test them later to see which ones are hot and which ones are cool, because those happen to accidentally have good alignment, and they put them in a separate bucket and charge more for them. Now, normally, they try to minimize this effect and say, well, it's close, maybe it's a 0.9, and this one's a 1.1, we'll both call them a 1, and off is a 0. But in a FPGA, maybe you could do something different. Maybe you can take advantage of those differences. Maybe you can take that variance, that quantum variance that was put into the chip when it was made, and roll that into your mathematical algorithms for your cryptography. And now, if someone steals your code and they steal your key, they still can't get the same result as you because they don't have a chip with the exact same mask alignment. It's a physically unclonable function. And if you really get into security space, that one is just bananas. It's also a little bit, put a caveat on it. As the chip goes through heating and cooling cycles, those properties change over time, so they may only last a few years. Okay, but the last point on FPGAs, and this is really important, is that they must be in the same die as the CPU. This gets back to don't trust the circuit board. If it's in a separate chip on the circuit board, that's good enough for a PC. It is not okay for a connected device. It's got to be in the same chip. You want to make them cut the top of the chip off. And the picture there of the Xilinx Spartan 6 is an example of a chip that has a couple of ARM cores and a big FPGA fabric around it. And that's exactly the type of thing we're looking for. The next big observation I have, all the big operating systems that we use today, that's Windows, Macintosh, iOS, Android, Linux, all of them, are called macro-kernel systems. Macro-kernels were developed in the 1980s, and this is the one where you have a driver, like for that printer, and you load it into the kernel. And they did this for performance reasons. In the 80s, the chips were not nearly fast enough, and if you had to talk to hardware, you needed to be right on top of it. In the 90s, they said, this opens up all kinds of security holes. There's got to be a better way. Let's try moving those drivers up into user mode and then remove them from the hardware, so they have to ask the kernel to do something and then talk to the hardware. It's tremendously more secure. And they actually successfully built multiple microkernels in the 90s, except they were still too slow. It's like 10,000 cycles to go from user mode to kernel mode. Every time you want to read a sector off a hard drive, it's not going to work. But the last time I checked, it was 2019. The chips are tremendously faster, and researchers have gotten the transition down from 10,000 cycles to about 80. Okay, performance is no longer a reason. The reason we don't use microkernels everywhere is inertia. You would have to go and rewrite all the drivers for these operating systems and probably rewrite your apps too, and that's just not going to happen. So as I think about microkernels, I think their day is here, but we need to start in markets where there's no legacy, and to me that sounds like IoT. Right? Every device is a new device, there's no software written for it, you get to start over. And this is where we should be exploring and experimenting with new types of kernels. And the goal here is to isolate your code as much as possible. An attacker is going to try to go to your app and use that to go to another, and if they can get into something in the kernel, you're done. But if you can move everything into user mode and isolate, you have a chance. Final piece is formal validation. Formal validation is really hard, but I predict this will be extremely valuable if you know how to do it. So there's a tool called Isabelle, which was created at Cambridge in association with, I'm going to blow it, there's some school in Germany whose name I can't pronounce. Right? They built a tool out of the math department, and the goal was, hey, we're trying to do these mathematical proofs by hand. Wouldn't it be cool if we had a software program that we could write a proof in, and then it would tell us if it worked or not? So they did this. In Isabelle, you can write a proof. It will tell you if your proof is internally consistent. You can take data and apply it to the proof, and it will tell you, yes or no, this data conforms to the proof. So it turns out you can model about 1 line of C with 20 lines of Isabelle. So there are kernels where they've stripped them down as much as they can, and I'm thinking of a particular kernel which is about 10,000 lines of code, and then you build a 200,000 line proof, and security bugs just start falling out of it. Right? This is the only way to take your really security critical code and know that it's going to be okay. Right? So my goal in bringing this up is that if you're worried about this space, or if you want skills that will be extremely valuable in the next 2 decades, formal validation, microkernels, FPGAs. That's the combination that's going to get the next trillion devices up and running in a way where we can actually believe that they're doing what we wanted them to do. So last slide. I left Microsoft 4 years ago. I decided this is the space I want to play in. So for about the last 2.5 years, I've been doing my own research on these exact same 3 subjects with varying degrees of success. I'm probably not as far along in FPGAs as I want, but I've been going deep into microkernels. I also think a lot about robustness, things like the Erlang Beam engine. What does it mean to have that running in these types of environments? And if anyone wants to talk about the future of operating systems, I would be happy to talk to you about it. And that's how you reach me. The new company is called Crichton Industries, down in New Zealand, and it's been a pleasure to talk to you today.